So we want to take a look at, let me see, so y equals x squared. We have the space between those two guys, and we are rotating about the y-axis. So I think we've already done this one, if not one very similar, where we just got y equals x squared. Of course, the intersection points are 0 and 1, and since we're rotating about the y-axis, it's going to look something like this. And if we wanted to, we could draw washers. So I don't know if you guys have this in your notes, or if you want to look back on the old videos of what that answer could be. I don't know if that pink showed up. Maybe I'll use a darker color for highlights. But we don't want to use washers with a width now. Instead, what we want to do are these cylindrical shells. So our shells, the height is going to go in between the functions. And then, of course, the shell is wrapped around the axis. And they are thin little tin cans. The width, or the thickness of the can, is going to be dx. And so now let's just pick out all of the pieces. So our volume, again, integral of dv. And so what is the dv? It's really the sort of surface area of these tin cans, of these shells, and then they have a thickness of dx. And so what is our area? We remember area for a cylinder is 2 pi r times the height. And because we are rotating around the y-axis, the radius is just going to grow as x grows. So the radius is just the x value. And the height now is determined by the distance between the two functions. So my top function is x. The bottom function is x squared. Distance between the two, of course, is then just x minus x squared. And I'm plugging that in. Our volume, I'm going to pull out the 2 pi and then distribute the x. So x squared minus x cubed dx. Last thing we need is to fill in the bounds. So the bounds are the radii. So the radii start at, the axis of rotation, so 0 for the x value, and then go all the way out to the largest x value of 1. So integrate that, check it against what you might get with the washer method. Should get the same thing. Okay, so let's set up a couple more. I want to do one, let's do one that you can't use shells for. And actually, this is a kind of an interesting one. Let's actually make it an improper volume, so to speak. Let's use this bell curve. So we've got y equals e to the minus x squared, y equals 0, x equals 0, and then, of course, up to infinity. And we are rotating again about the y-axis. So when we draw this, e to the minus x squared is our standard bell curve. But now we are actually making like a bell out of it. We are rotating it. So it's going to just go around. And then, of course, we've got it rotated around. So it's like we took this right half and then just flipped it all the way around. And of course, we're bounded below by the y equals 0, by the x-axis. And so we could try to think, again, so what's going on with this guy in terms of the washer method, or even the disk method in this case? There's no or there's no hole in the middle. The problem is, if I use washers, the height of the washers would be dy, which means I would need to solve this equation for x, which we can do, but it's not going to be pretty, right? I would have to take a natural log of both sides, then divide by a negative sign or multiply by a minus sign, and then take a square root. So we would get something like a square root of a natural log. And I don't know about you guys, but I don't know how to integrate a square root of a natural log. That's something we actually haven't seen. If it was don't confuse your natural log rule. Sometimes this is a common mistake where if it's like 1/2 times a natural log, we can put the square root on the inside, right, on the inside of the argument, make it natural log of something to the 1/2 power. But if I take a whole natural log and then take the entire thing and square root it, there's like nothing we could do with it. And so integrating that is going to be a pain. If I were to just try to integrate this guy as well, I can't integrate e to the minus x squared either. We would need a fancy trick. But because we're doing this rotation and making this full bell volume, we can actually get something meaningful out of this. So let's draw our shells. So the bottom of the shell is just going to sit on the x-axis. They've got a thickness of dx. And then again, the radius starts at 0 and then just goes out to whatever x value. Volume is dV. I am messing up all my differentials. A dx, excuse me. And then, well, what is our area? We will have 2 pi, r is x, and then now we need our height. And the height in this case is pretty easy. It's just 0 up to e to the minus x squared. And then we've got our differential dx. And then the radii, smallest shell, is going to be, infinitesimally right around 0. Then as I grow these shells, our upper bound is, of course, infinity. And now this is something we can actually do. Let's go ahead and do this one real quick. We can do this with a u sub. So if I say u is, let's see, how do we want to deal with the minus? Let's just go ahead and put the minus in our u sub. Say minus x squared. And then our du is negative 2x dx. And so minus 1/2 du gives our x dx. And then we can integrate this guy. Let's pull out the 2 pi. We will have times a negative 1/2. And then we will have x dx is our du, and then our e to the u du. I'm not going to worry about the bounds. I think it would just switch. We would have 0 to minus infinity. Let's just go ahead and integrate and put everything back in terms of x. So this is just going to be negative pi, sorry, no more integrating, times e to the u, of course, and then whatever the bounds are. So just negative pi e to the minus x squared, and now 0 to infinity. What happens when I plug in infinity? So of course, to do it properly, we should take the limit, but I could plug in a t there, a dummy variable, and then take the limit. What's the limit as e to the minus x squared goes to infinity? Just gives me a 0. So I'll have 0 minus negative pi. E to the 0 is just 1. So our total area, total volume, is just pi for that guy. Any questions? Anyone still writing?
Can you explain one more time, sorry, why the upper bound is infinity?
It's just because we want to take our shells. I didn't set a hard limit on where we want to take our shells. So our shells are just going to keep going into these really broad, flat shells and integrate all the way out to infinity. So it is like this bell that's rotated, but the bell tapers off and then the ends of the bell never stop. They go out to infinity. And we want the total volume underneath it.
That makes sense. Thank you.
Okay. So let's just do one more, and then let's get started on the project here. And let's do one where let's do one with like the opposite direction. So our shells will have a thickness of dy. So let's rotate about, let's see, about y equals 0, x equals 2. That's a vertical axis. Oh no, I didn't have an example. I was looking for one of these. Oh no, there's the one I wanted to do. This one's on the homework. And I don't know, so I just kind of saw this one on your guys' homework. I wanted to pick out an example of something that was rotated around a horizontal line. And so we've got y equals x cubed and y equals square root of x. I feel like we've seen something similar to this. We've played around a lot with these, polynomials of degree 1, 2, and 3, as well as either y equals x or y equals square root of x. And then what are we rotating? We're rotating about y equals 1. Sorry, let me move that. This is going to be one of those ones where you could probably do either way. You could probably do shells, or you can do washer method. For the sake of the lecture, let's go ahead and do cylindrical shells and see how this is going to work out. Primarily because we've got shells now going in a different direction, and our rotational line it's not one of the axes. It's y equals 1 now. So we've got to make sure we're careful when we determine the radius on this guy. So let's draw it. Let me see. So we will have our x-axis here, x cubed and square root of x. So x cubed, it's going to look pretty similar to x squared, at least between 0 and 1, just in shape. Hopefully everyone can kind of see that the intersection points are 0 and 1. Since 0 is cubed and square root of 0 is both 0. Likewise, 1 cubed and square root of 1, both 1. So there's our x cubed, our square root of x. So we want this region, but we are rotating about the line y equals 1. And so it's going to look something like this. Sorry, this was homework number 9. So washers would work fine with this guy. You would have your dx's, and actually the washer method, if you're comfortable with it, may actually be a little bit quicker, namely just because the width of the washer is going to be a dx. And since I have everything solved in terms of x, you wouldn't have to do any work there. Let's check and try to see if we can set this up using a shell method, though. So our shells are going to look like this. And now the thickness of these horizontal sideways cans is dy. And we need to work out the both the radius and the height. So our integral, it's our typical setup, a dy now, and our area is once again 2 pi rh. And so we need to figure out our r and h. Let's do r first. Let's solve for our functions. Since we have things in dy, let's go ahead and solve these guys in terms of x, or solve for x in terms of y. So of course we'll have cube root of y as 1, and then y squared as the other one. And so now what is our radius? Our radius, the smallest radius, is, well, I mean, the distance is 0, but the radius is going to go from 1, and actually let's measure downward, 1 down to and actually, let's see, where's our best radius? So we're not going to hit that guy. It's actually going to go to the outermost function. So the radius goes from 1 down to this function. So what is our radius? That distance is our y value, and I'm actually wondering now if this method will even work. And so this distance here is going to be 1 minus y. The height of these guys so the height is this distance here. And when we're doing things in terms of y, it should be the right function minus the left function. So this right function was x cubed, which is going to be cube root of y minus the other function, y squared. Everyone see that? So let's set up this integral. Where were we at? We've got a dy. Our volume is now 2 pi. Our radius was again 1 minus y times cube root of y minus y squared dy. And now here's the tricky part. We do gotta mind the bounds. And since we're integrating with respect to y, we want to know what are the bounds for the y. And it's easy to kind of overthink this. The y values we're integrating start at 0 and go up to 1. In some sense, it's almost a little backwards when with these other ones that we've done. Because I've started at the center and made these shells grow outward, really what we're doing here, since I'm integrating with respect to y, I'm starting with the outermost shell and then integrating, summing up inwards and adding up these shells as my radius shrinks, really. So what do we get with that? I almost want to check ourselves with this and do it both ways. So let's go ahead and do that. Let's see. So we'll have our 2 pi. I've got 1 minus y. So we'll have y to the 1/3 minus y squared. Y to the 1/3 minus, so that'll be y to the 4/3, and then plus y cubed dy, 0 to 1. Let's do the integration. 2 pi, so 3/4 y to the 4/3 minus 1/3 y cubed minus 3/7 y to the 7/3 plus 1/4 y to the 4th dy. Oh no, sorry, not dy. 0 to 1. 0 is not going to matter. And so what do we get when I plug in 1? We just get a bunch of fractions we got to add together. 3/4 minus 1/3 minus 3/7 plus 1/4. With all that. So 3/4 and 1/4 is 1 minus 1/3. So we'll have 1 minus 1/3, which is 2/3 minus 3/7 is a little weird fraction. So it looks like we'll have to find a common denominator, which is 21. So we've got 14 over 21 minus 9 over 21. So I'm getting 2 times 5 gives me 10 over 21, and that pi hangs out. Let's check ourselves. Let's go through this real quick, just to check our washer method on this guy. So let me keep the same picture. Let's try to draw a washer. So width there is dx. So on the washers, what is the inner radius? Is it showing up on the video, that light color? Yeah. Our little radius is going to be 1 minus y, which is y up to this inside curve, which was our square root of x. So 1 minus square root of x. And our outer radius should have been 1 minus x cubed. And so what does our washer method give? We should have the volume is pi times 1 minus x cubed squared minus 1 minus square root of x squared dx. And the bounds for x's now still go from 0 to 1. So this actually looks like at least we'll have a 6 power there. So that's promising. So when we integrate that power of 6 again, we'll get a power of 7, which will give us that 1/7 in the denominator. So let's go through the algebra, or at least get it started to see if we'll get the right thing. 0 to 1, bunch of algebra. I'm going to go through it quick. 1 minus 2x cubed minus plus x to the 6th minus 1 minus 2 squared of x plus x dx pi 0 to 1, 1 minus 2x cubed plus x to the 6th. Let's distribute that minus sign. And any like terms, it looks like I've got 1 minus 1. Those will cancel. Everything else looks like it's still going to be there, and we need to integrate. So what do we have? We've got a minus 2x cubed plus x to the 6th plus 2. I'm just going to write that as x to the 1/2 minus x. All of that with respect to x. 0 to 1. And then integrating, we've got minus 2/4 x to the 4th plus 1/7 x to the 7th plus 2 times 2/3 x to the 3/2 minus 1/2 x to the squared. 0 to 1. And then now, again, the 0 I plug in doesn't matter, just the 1, and it's going to pick out the coefficient. So I've got minus 1/2 plus 1/7 plus 4/3 minus 1/2. We plug in our 1. And then, fortunately, those numbers aren't similar, but our denominator looks like it should be the same. So minus 1/2 and 1/2 gives me a -1. I'm going to write it plus the 4/3. I'm going to add the easy fractions first and deal with the 1/7 denominator at the end. So minus 1 is 3/3 plus 1/4, or 4/3, excuse me, is 1/3 plus 7th. And so what is that? So times 7 will give me 7 plus 3 over 21 times pi. Oops. So 10 pi over 21. So good. Both methods work, and we get the same thing. And so there you can kind of compare whichever one you thought was easier. I mean, this one I went through fast. Kind of also depends on how comfortable you are adding all these fractions together. All of them get a little messy. So sorry if that was a little fast. I'll give you guys a second to catch up on writing any of that if you guys still are. All right, any questions, or is anyone still writing? So the harder part of that with shells was kind of understanding the radius. When our radius isn't just right about the x-axis or the y-axis, it's a little weird thinking about the shells because we've got this inside function and outside function. And if you kind of think about it, well, the radius of the shell, it always goes out to the outside function because I got to hit that, and then the side of the can is what encodes the information between the two curves. So the distance, we really only needed to write as 1 minus y for that radius of these shells. Since the height, going from the x-axis up to that bottom curve is just a y, and then the distance between the line 1 and that is going to be 1 minus y. Okay, so let's go ahead and get started on this project. Let me go ahead and turn off, let me stop the recording.